So uniformly, the magnitude of the vector is constant everywhere. So if you take, for example, this line, I'm sorry. If you take this line, this line, this line, they have the same magnitude, okay? And this is constant. And the same, for example, if this is V is unit, then everything is unit vector, something like that. Okay, so flux means, flux, let's say the symbol denoted by, the flux denoted by, let's say E, phi E, it means that how many lines pass through this rectangular, okay, is the number, let's say, is the number of lines passing through the rectangular. Let's say this one, rectangular. So this number is equals to V, the magnitude, times the area of rectangular. So this is the area, this is the area of rectangular. Okay, and this is equal to the magnitude of the vector. So, oh sorry, let's say this is V. Okay, this V is related to the flux of vector V. So if we have V, we replace V by E. This is electric field. So it means that the flux of E, electric fields, is the magnitude E times A. Okay, that's the flux of electric field. So in general, these, for example, fluxes is not, let's say, perpendicular. Yeah? So you see that this fluxes is perpendicular to the surface, yeah? The surface of rectangle, this rectangular. Okay, it means that it's parallel to the normal vector of the surface, rectangular surface layer. Okay, if the lines make an angle, like this. This one, for example, this is theta here, and then the normal vector of the surface, like this. This is perpendicular to the surface. So in general, the flux of E is E vector dot A, where A vector is the area times the normal vector. Okay, so area is basically a vector quantity. So this dot, as you have already known, that this should be the magnitude of A, the area of the rectangular times cos theta. So the theta is the angle between A and vector, normal vector. Okay. So we still think that this A, the magnitude is A, the magnitude of the vector E is constant. Okay. Any question from here? Any question? Okay, if not, I continue. So what about if, in general, what about if E is not constant? Constant. So it means that VA infinitesimal A is E dot dA. So dA here is vector is dA times and hat is lower factor of the surface. So in general we have V equal integral E dot dA. So this is the flux formula for electric field. So, okay, then from this flux, we can formulate the Gauss law. Gauss law. So Gauss law, it means that in general, this is the open surface, this one. This is the open surface. Open surface. This is also open surface. So Gauss law is related to the closed surface. What is closed surface? For example, in general, you can imagine a sphere. Sphere, for example. This is an isotropic. Isotropic. Isotropy means we can see in every direction, have the same shape. Well, we can say this is the perfect sphere. Yeah? Perfect sphere. It means the isotropy means the same, exactly the same shape in every direction. What it means that if you see a sphere from everywhere, it's still sphere. Okay, that is what isotropy means. For example, for non-isotropy, for example, if you see the cylinder here, this cylinder with cover here. Cylinder with cover. So anything else? You can also imagine a torus, a donut, torus. Sorry. torus. That is so far the two-dimensional closed surface. Okay. So in general, you can make any closed surface. For example, this is closed surface. Okay. Then you have, for example, well, this is Q here. And then this Q have a electric field passing through its surface. The boundary of the surface, this one. So the Gauss law means that the closed surface from the closed surface, the flux from the closed surface equals to Q enclosed over epsilon 0. So this is the vacuum permittivity. Okay. What is Q enclosed? I will give an example. For example, number 1. We have a point particle. Let's say this one. This is Q here. So let's say I take this Q in the center, yeah, in the center of sphere. Okay, this is the center, US English, yeah, center of sphere. So this is Q enclosed. Sorry, this is Gauss surface. This is Gauss surface. Sorry. So this is Gauss surface, and this surface covers only one charge. Okay, so Q enclosed. How many charges? 1, and the magnitude of this charge is Q, big Q. Okay. Okay, the second example, we have two charges. Two charge particles. So we have, let's say, Q1, and this is Q2. Okay, I make this Gauss surface. How many charges that this surface covered? 2, yeah? Okay, so this Q enclosed is how many charges? 2. So this is the summation of the Q's. Little Q1 plus Q2. If you have many charges, everything until Qn, yeah, so this Gauss surface, this surface still covers n charges. It means that Q enclosed is summation Q1, Q2, plus dot Qn. Okay? That means this enclosed. How many charges that the surface covers? Okay. So, for example, this Gauss surface, the red one, okay. For example, if I take another Gauss surface, the blue one, let's say here, this is also Gauss surface. How many charges which this surface, this blue surface cover? How many charges? How many charges?
0.
Yeah, none. Yeah, none. So it means that this surface doesn't cover any charge. Okay, so this Q enclosed is 0. Okay. This one also, for example, if we take any arbitrary Gauss surface, yeah, that doesn't cover any charge, so this Q enclosed also 0. Okay. Okay. So let's consider again this point particle. So we consider the red one, yeah, the red Gauss surface. So this Q enclosed is Q. Okay, if the radius of the surface is r, little r here. So r here, it means 4 pi is 2 squared. Okay, the area of the Gauss surface, Gauss surface, a sphere is 4 pi 2r. Okay. So Q enclosed is Q. Okay, this one. Then according to Gauss law, that this one. Okay. Integral for closed surface. So this is a for closed surface. Because we only consider at the boundary, I mean, only in this surface, so this E here equals to and dA is equals to A, right? Okay. So this is E times 4 pi r squared. And this is Q enclosed. This is Q over epsilon 0. So we will obtain the field for point particle. Okay. We re-obtain. So this is the electric charge of a point particle. Okay, any question?
This only applies for point particles?
No, in general. So, okay, let me explain. Why point particle? Because point particle, as you see, the point particle, so this is depend only on the radius of the surface. It means that a point particle system has a spherical symmetry. Okay, it doesn't depend on theta or phi, something like that. So everything, I mean, if you, for example, let's say in this one, E here is exactly the same as the E in here. So this surfaces has, we call it, let's say equipotential. We'll discuss about potential. What is potential later? Equipotential. So a point particle system has a spherical symmetry. So it means that Sultan is already okay. So what I will say. Okay, the particle system, a point particle system, has a spherical symmetry. It means that it is easier to solve. Easier to solve. Easier to solve Gauss law. What about for many charge system? So many charge system like this, the system is no longer spherical symmetric. It's no longer spherical symmetric. That's why it's very difficult to solve Gauss law. So Gauss law is more general law than Coulomb's law. Yes, but it is easier to solve it under symmetry case. So we have situations, for example, like this one, the point particle, a point particle, for example. A point particle has a spherical symmetry, so it is easier to solve the Gauss law. But in general, for example, in n-charge system, this system is no longer spherical symmetry, so it is difficult, very difficult. Okay. So what is the well, the properties of this symmetry? Let's say this one looks like the point particle is here like this. Okay. Okay, this one. So this is basically spherical symmetry. What about, for example, two charges? Two charges. Let's say dipole. For example, we have, so there is a Q here, and dipole there is a Q and minus Q. Okay. So what is the lines of electric charge? The lines of electric fields look like. So let me draw for you. So there is P here, for example, D, the distance between these charges. Sorry, just 1 second. Okay, this is for example for dipole for two charges system, and this is no longer a sphere. Okay, this is not sphere. Okay, you can draw, for example, again two charges have the same sign, for example, plus Q and plus Q, for example. This is also like similar like this, but they are repelling each other. This one, this one. Something like that. And also this is not a sphere. No sphere, okay? Sorry, not this one. Not sphere. Okay, any question? Any question? No question.
Not yet, sir.
Practice by drawing 3 charges. What is the lines of electric fields look like? Okay. What about 3 charges? Sorry. 3 charges. Yeah. So make on your own before you sleep. Yeah? Before you sleep, and then it will make you sleep. For example. Okay, there is no question. Okay. So I will give you another example with symmetry also. I say the third is let's say a sphere, yeah? A thin shell, a thin sphere, yeah? So this is basically a sphere. A sphere only this shell, yeah. The shell, only the shell. Only the shell. shell, thin sphere, only the shell, without what is yeah, in bahasa this means kulit bola, kulit bola, tanpa isi, without inside the isi. Yeah, without content, without content. So for example, this is Q. Okay. The charge is Q, could be positive or negative. And then they have the radius big R. Okay. So sigma here, the density of the charge, the area density, charge per area. Charge per area. So the area of the thin sphere is Q over 4 pi big R squared. Okay. So I have assumed that this should be uniform. Just for simplicity, okay? Uniform, it means constant. Constant. Okay. Okay, I redraw again the sphere here. Okay, with radius R. If we make Gauss surface, okay, the electric field, we have I divide the region. This is region 1 and region 2. Yeah. Okay. So region 2, for example, this is R greater than or equal to big R. Okay. It means that the Gauss surface, the radius is greater than R. Okay. So I make this Gauss surface. This is R here. Okay. If you want to take to the bathroom, okay, please. Okay, this R here in this second region, this 2 region, the radius of this Gauss surface is greater or equal than big R. The big R is the radius of the sphere, the thin sphere. Okay. So what this in this case? So integral A dot dA, it means that this is equal to A integral dA. Okay. And this equals to E times 4 pi little r squared, yeah, because little r is the radius of the Gauss surface. This is the radius. R is the radius of Gauss surface. Okay. How many charges that covers this, which is covered by this Gauss surface? So this is equal to Q enclosed. Q enclosed, this is Q here, BQ over, okay, this epsilon 0, this vacuum permittivity. Then we get that A in the second region, this is equal to Q 4 pi epsilon 0 R squared. This is for thin sphere. Okay. And then for the first region is R less than big R. So again, R little r here is the radius of Gauss surface, and the capital R here is the radius of the sphere. So what about this little r less than capital R? So we make the Gauss surface inside the sphere. Let's say this one. This is also R. Okay, and this is this one. How many Q enclosed? How many charge that covers? Anyone?
Sir, is this
Yes?
the shell is inside the Gaussian surface?
Gauss. So let me continue. Just okay. So this Q enclosed here, we don't have any charges, right, inside the sphere. Okay, so it should be 0. Then this E1 mean Roman I is 0, yeah. Okay. So the field, the electric field inside the thin cell, inside the thin sphere is 0. Okay. Okay. Any question? You have a question? Anyone?
Is the electric field in the form of a thin shell?
Is sorry, what is your question?
So the thin shell is the electric field.
The potential.
I'm confused. What's the Roman numeral 2? Roman numeral 2.
E2 you mean? This
Yeah.
one.
Yeah.
This one.
Yes.
Which part you are confusing?
Where is the field coming from?
The field. Oh, okay. The field coming from. Okay. So because we have charges distribute on the surface of the sphere, so the field coming from the sphere, the shell of the sphere. So Q distributed uniformly on the surface. Okay. So the source charge is on the shell or the skin of the sphere, something like that. Is that clear for you?
Oh, okay, clear. So that's why when the shell is inside, there's no charge.
Yeah, there is no charge inside there is no charge inside the sphere because we have only thin sphere, only shell. The thin shell of the thin shell of sphere. Okay, this is the case of continuous charges. So the sphere for rigid sphere and also only we'll discuss the rigid sphere later, maybe after this one. So for thin sphere, I mean thin shell sphere, the charge only distribute on the surface, not inside the surface. Okay, because we have only thin sphere, only the shell, yeah, the shell of the sphere. Okay, anyone?
Is the Gaussian surface also just a thin shell?
Sorry?
Is the Gaussian surface also just a thin shell?
Yes, yes. Gaussian surface. If we talk about surface, it is a thin shell also. Yeah, exactly.
Okay. Okay. Thank you.
Yeah. So if we draw the electric field, in this case, we have E in the vertical axis and this R in the horizontal axis. Let's say Q is, sorry. Okay. Let's say Q is positive, yeah. So as you see that this is capital R here is the radius of the sphere. It means that for R less than capital R is 0, yeah. This is 0, this one. And then this is Q squared over 4 pi epsilon 0 capital R squared. Okay, sorry, not Q squared, sorry. This is only Q. So exactly at the point where little r is r equals to capital R, only this one. Okay, and then sorry. Something like that. Okay, so there is, if you have already studied about discontinuity, so this is discontinued. This. Discontinued at this point. Okay. Okay, that's the thin sphere. What about the rigid sphere? Rigid sphere. The fourth example, rigid sphere. rigid sphere, I think. Oh, sorry, maybe it's the correct is solid. I think it's solid sphere. Solid sphere. Sphere with content, with filling. Maybe filling is the correct one. Solid sphere. Okay, I draw again the sphere. The radius is capital R. Okay, and this is the center. Let's say this is Q here. So for the solid sphere, we talk about the volume density. The volume density. So it means that this is rho, is the Q over the volume. So the volume is 4 pi over 3 R to 3. Sorry, capital. Sorry, capital R3. Okay. Similar as the thin sphere, we have two regions. Yeah, this is the first region, and this is the second region. So the first region, so the second region is R greater or equal to capital R. Okay, so we make the Gauss law outside the sphere. Okay, so this is the Gauss surface. We make the Gauss surface outside the sphere. So this is the Gauss surface, which is also a sphere. Okay. Yeah, as your friend said, that this is also a thin sphere, this Gauss surface, only a surface. Okay. So we have E this is equal to E times P R squared. Okay. What about Q enclosed? In this case, Q enclosed is Q over epsilon 0. Then we get similar expression as the thin cell. Yeah, so the electric field outside the sphere in the solid sphere and also thin sphere have the same form, as you see. This one. Okay. So in the first region, R less than capital R, they have the same on the left hand side of the Gauss law is the same. So basically, we make the Gauss surface, this green one, the radius of the Gauss surface is also R in this case. Okay, but Q enclosed here Q enclose. How many you have? So this is basically integral rho the volume. So the volume of this one is something like 4 pi r squared rho dr. Okay, so because this is a constant, sorry, I forgot to mention that this rho is constant. It means that the charge is distributed the charge is distributed uniformly in the sphere. Okay, rho is constant. So because this is a constant, this is equal to 4 pi r to the 3 over 3 rho. Okay, and this is equal to 4 pi r3 r to 3, and then this is q over 4 pi over 3 capital R. So this q enclosed here equal to, so this is, yeah, we can divide this one by 1, okay? Then we get this is equal to q r to the 3 over capital R to 3. Okay, so this is q enclosed. So if we put this one enclosed over epsilon 0, then we get E equal to Q over 4 pi epsilon 0 R3 times R. Okay. So this is non-zero. Yeah? So the electric field inside the solid sphere, yeah, is non-zero. So it differs from this one, from the case of thin cell, thin sphere, yeah. Charged thin sphere. This is a charged solid sphere. So so the point particle, there are so many such that they form a solid sphere. Okay. So if I draw the electric field against versus R, we get that this for R equal to the capital R here, so the field becomes Q over 4 pi epsilon capital R squared. Okay, so this is, so you see that this is a linear, yeah. E depends linearly on R. Okay, so this should be, it's a line, straight line, and then after passing through the sphere, we get 1 over 2 squared, 1 over R squared, sorry. Okay, this one. So again, that this is also, well, this is continue. Sorry. This is continue, but not differentiable. Okay. Any question?
No question, sir, I think.
No question. Okay. Okay. Clear, yeah? Sorry about that. Okay. So I will continue with another example, the fifth example. Fifth. Okay. First example. One better. Very long road. Charge, very long charge road. So we have one-dimensional case. Okay. This is very long. Sorry. Very long, it means that we have a length, let's say capital L, and the width is, let's say D. It means that very long, it means that this L is much, much greater than its width, D. Okay. So in this case, for example, if we consider, let's say this R here, okay, the distance from the cylinder, the rod, and the point P, for example, where we want to know what is the expression of the electric field on P. This is also means that L here, the case is much, much greater than R. So we can say that this R here is the radius of Gauss surface. Okay. So in this case, the very long road, if we have this condition, this, let's say 1, this is 2 here. So we can approximate that this rod has cylindrical symmetry. Cylindrical symmetry. Okay. This is, let's say, dot lines. These dot lines represent the Gauss surface. Gauss surface is cylindrical, thin cylinder. Thin cylinder with cup. with cup. Cup, these two cups here. This cup. Okay. So the electric field, in this case, let's say, so this lambda is the density charge density. This is Q, let's say, over R, over L. Okay. It's constant. And also it means that it is distributed uniformly, constant. Sorry. Constant. Okay, so this integral, this one, E dot dA. Okay. So the electric field in this case, the direction is outward. Yeah. So they outward, so it means that they becomes far away from the axis. Okay, outward to the infinity. Yeah, outward. So, okay, so we divided this field. This is, let's say, E1. Also outward this, sorry. Sorry. Let's say this is E, okay. And this is also in here, also this one, E. And on at the cup, this is E also. Okay. So this should be E plus integral E. I'll explain it to you. E so the first term is first cup. This one. This cup here, the cylinder cup. And then the third term is the second cup, the cup 2, let's say. And this is cup here. Sorry. This is cup 1, and this is cup 2. Sorry. Sorry. And then we have cylindrical cover. This is cover. This cylinder cover, okay? This one, this cover. So you see that this normal factor here, in the first cup and the second cup, yeah. So this is 0. This is 0 because the normal factor is perpendicular to the electric field at the cup. So we only left with the second term, which is the cover of the cylinder. And the cover of the cylinder, you know that this is E 2 pi R L. Okay. And this is Q enclosed. Sorry, okay. Q enclosed over epsilon 0. And Q enclosed is lambda L over epsilon 0. So we get that for very long rod, a charged very long rod, the electric field around it near the rod is, we can say lambda over 2 pi r pi epsilon 0. Okay, if we make this equal to q over epsilon 0, so this is q over 2 pi epsilon 0 L R. Okay. Any question? Any question? Any question? No.
No, sir.
Okay. I hope you understand what I'm saying. So the cover means also seat, yeah? Seat or casing cover, the cylinder cover, cylinder seat. Okay, the sixth example. The sixth example. Sixth example. Is let's say 6. It's a very long cylinder. Very long cylinder. Very long charge cylinder. Let's say, yeah, you can say, well, to make the time we're running out of time, solid cylinder. Okay, so this is this one. Okay, this is the length L. We have the radius is R0, for example. Yes. So it means that very long rod means that this R1 is much larger. The length is very long compared to its radius. And then if we take, let's say this is the axis, the cylinder axis. Okay. This is R here. This R, oh, sorry, this R, this L here, also much larger than the radius of Gauss surface. Yeah. So it means that we have only to consider around the cylinder, the seats, around the cylinder. Sorry for some problem with the computer. Any question about this one before I continue? So we have two regions, this inside and outside. Yeah. So we can take the cross section of this cylinder. We can consider like this. This is R0, yeah, and then the cylinder axis outward to the board, yeah. And let's say this is R is the radius of the Gauss surface. So for the second region, where R greater or equal to this capital R0, the same as the previous one, this one is this A, and this is, oh, sorry, I forgot. This Q here, the charge distribute uniformly, yeah, in the cylinder, because this is solid cylinder, they have a content, something like that. And this, we have the charge density, volume charge density is Q over P capital R squared L. Okay. Okay. This one is also E times 2 pi R0 L. Okay, Q and close. Q and close. This is integral rho times dv, okay? So this is equal to rho times P R0 squared times L. So basically this is Q, right? This is Q. I'm sorry. This is not R0. This is 2 pi R L. Sorry. So basically, if we use the Gauss law, we will get this. This is Q over 2 pi epsilon 0 R. This is outside the cylinder. In the inside cylinder, this R less than capital R0. So we have integral E of dA is equal to, so this is the Gauss law, Gauss surface outside, and this is inside the Gauss surface, both, let's say this radius R and R. This is equal, yeah, pi r L. Okay, but Q and close means that integral rho dv, but here is a rho integral rho 2 pi r L dr. So this is basically is rho. Sorry. So this is basically rho L integral rho L 2 pi, sorry, 2 pi, sorry, 2 pi L, sorry, 2 pi L integral rho R dr. So because rho is constant, so I put outside here. Okay, so this is equal to pi L rho R squared. Okay, but this is rho here, the same as P L Q over P R0 squared L R squared. Okay, so this one becomes Q squared over R capital R squared. Okay, so we put into this one to go slow, so we get that this E here, Q enclosed over 2 pi RL times epsilon. So this is Q R squared over R0 squared, capital R0. This is 2 pi epsilon R L. Okay, so this is Q over 2 pi epsilon 0 R 0 squared L. Okay, this is R. Okay, so this is, let's say this is 1 and this is 2. Yeah, this one. Okay, so E1, yeah, it's proportional to this Gauss radius. Okay, the surface, the radius of Gauss surface, this little r here, and then but in the second region we have this E2 is proportional to 1 over r, where r is the radius of Gauss surface. Okay. So this is for solid cylinder. So you can draw the E against R. You get this is 0 and this is R0. Okay. So they basically they will, Okay, let's say this one is Q over 2 pi epsilon 0 R0 L. This one. So it will be linear until this one, and then like this. Okay. Any question? Any question? Okay, I will review the summary. I will summarize the lecture today in bahasa. Jadi dalam hari ini kita belajar tentang hukum Gauss ya untuk elektrostatik. Jadi awalnya kita memperkenalkan yang namanya definisi dari flux ya. Flux listrik ya, yang didefinisikan sebagai V di sini. Ya. Jadi V di sini secara umum dia tidak konstan ya, jadi dia harus berupa integral ya. Dan dia merupakan dot ya, jadi artinya ini adalah besaran skala. Nah dari flux ini itu saya membahas beberapa kasus untuk memecahkan persamaan Gauss. Jadi persamaan Gauss itu sifatnya lebih umum ya dari persamaan kolom karena dia diturunkan dari prinsip yang lebih umum yaitu dari matematik ya, dari geometri. Cuma memang kalau untuk kasus yang tidak punya simetri seperti yang tadi saya bilang seperti bola, silinder atau yang lainnya, itu lebih susah memecahkannya dibanding dengan yang punya simetri gitu ya. Jadi simetri bola, simetri silinder itu kita lebih mudah. Tadi kita ambil contoh untuk simetri bola dan silinder ya, yang nanti umumnya dipakai di ujian. Nah, jadi bukannya kita tidak bisa memecahkan persamaan Gauss, misalkan untuk partikel banyak ya, 2 partikel, karena 2 partikel itu dia simetrinya bukan lagi bola, tapi bentuknya yang lain gitu ya. Sedangkan yang simetri bola itu cuma yang di 1 partikel saja. Gitu. Seperti itu. Jadi dapatnya seperti ini. Nah, jadi kalau untuk 2 atau lebih itu seperti saya ambil contoh untuk yang mana ini ya dipol gitu ya. Ini Anda lihat di sini gambarnya dia bukan merupakan simetri bola ya. Jadi garis-garis gayanya dia tidak membentuk bola. Tidak bergantung pada R saja, tapi pada theta ada ya. Jadi dia bukan lagi simetri bola, makanya itu lebih susah untuk dipecahkan gitu. Lebih mudah pakai kolom. Kemudian Anda 3 dan 4 Anda coba sendiri. Kemudian saya juga membahas tentang bola ya, tapi hanya kulit bolanya saja, hanya shell-nya saja. Gitu. Jadi dia sigma ini adalah rapat permukaan per area, per luas ya. Jadi dianggap uniform ya, tidak konstan, maksudnya tidak berubah-ubah, tidak bergantung R atau waktu gitu. Jadi diambil dia uniform gitu. Jadi artinya dia terdistribusi merata, kekuatan itu di kulit bolanya gitu ya. Jadi ini kita bagi 2, itu ada 2 daerah, pertama di luar dari kulit dan di dalam kulit ya, kulit bola maksud saya. Thin sphere ya. Nah, jadi kalau untuk di luar bola itu bentuknya sama untuk medan listriknya ya, untuk di daerah kedua itu 1/R kuadrat gitu ya. Sama persis dengan ini karena ini sama-sama simetri bola. Cuma yang membedakan dia di daerah pertamanya itu karena tidak ada muatan di situ, itu S1-nya jadi 0. Oke. Nah, kemudian kalau dia itu benda bola pejal gimana? Jadi kalau kita tinjau juga ya di sini rho-nya itu dia juga konstan, jadi dia ada uniformly istilahnya distributed, jadi terdistribusi secara uniform. Dan ternyata untuk daerah kedua itu juga sama ya, jadi mirip seperti partikel titik gitu ya. Nah, yang membedakan itu nanti yang di dalam bola ya. Nanti di dalam bola itu dia tidak lagi singular 1/r², tapi dia sebanding dengan R. Jadi mana R di sini adalah jari-jari dari permukaan Gauss-nya. Ya, gitu. Jadi kalau Anda gambarkan seperti ini ya, pertama linear ya sampai R besar, kemudian dia ke 1/r² gitu ya. Kemudian yang kelima ini contohnya ini adalah yang mempunyai simetri silinder ya. Simetri silinder itu misalnya kita ambil kawat yang sangat panjang ya, di mana lebarnya D ini itu jauh lebih kecil dibanding dengan panjangnya gitu. Kemudian yang kedua, kalau saya tinjau radius jari-jari Gauss di sini, ya, yang R kecil di sini, R kecil juga itu jauh lebih kecil dibanding dengan panjang dari batangnya, sehingga itu bisa kita dekati dengan simetri silinder. Asal itunya sangat dekat gitu. Nah, jadi didapatkan E-nya itu adalah seperti ini gitu ya. Kemudian yang terakhir itu juga sama, jadi ini analog ya sebenarnya. Jadi silinder padat yang sangat panjang gitu ya. Jadi dibagi dua juga daerahnya, ada daerah satu yang di bawah, yang di dalam silinder sama daerah dua gitu ya. Ini juga sama pendekatannya, jadi panjang silindernya itu jauh lebih besar dibanding dengan radius tutupnya, cap itu tutup. Kemudian yang kita tinjau L-nya itu juga jauh lebih besar dibanding dengan radius Gauss-nya gitu ya. Sama. Jadi ini untuk kasus daerah 2 dan 1 ya, juga sama. Nah, daerah 2 ya kita bentuknya seperti ini, itu mirip seperti tadi yang batang ya. Kemudian yang daerah pertama itu ternyata sebanding dengan R gitu ya, seperti ini. Yang daerah 1. Sehingga didapatkan kalau saya gambar dia itu linear, dia kemudian 1/r gitu, setelah R0, di mana R0 itu adalah jari-jari tutup silinder. Ada pertanyaan nggak sejauh ini? Cukup jelas ya?
Cukup jelas, Pak.
Cukup jelas, oke, good. Terima kasih banyak. Oke, I will inform you maybe tomorrow ya, whether we could whether on Friday we will have a tutorial session, tutorial class. Tomorrow I will think about it, and then also for the assignment, I will inform you tomorrow. Okay? Okay, guys. Thank you very much. See you tomorrow. Thank you. Don't
Thank you
forget.
very much. Have a great day, sir.
Makasih, Pak.
Okay. Yeah. Okay.
Thank you, sir.
Okay.
Thank you, Pak. Have a good day.
Thank you, sir. Thank you,
Makasih,
Pak.
Pak.
Thank you, Pak.